Hi, and welcome back. This is the third video for our first lecture, which is on sort of a hodgepodge of chapter 15 and 16, um, discussing some of the properties of waves. Now, in this lecture, what I'd like to do is to further examine some of those properties, and we're going to start with a little bit of terminology. Because in the last two videos, we sort of established the idea of oscillations, and also, we investigated some of the basic properties of waves. For example, the relationship between the speed of a wave, which we'll call v, its frequency, and its wavelength. We also looked at a specific case of a wave on a string, and came up with the wave equation using that, and then looked at the relationship between the physical properties of the string and the speed of a wave on it. Now, that said, what I'd like to do today is to sort of continue along with some terminology, and we'll start here. Now, I know we've talked about the different types of waves that are, transverse waves, longitudinal waves, torsional waves, and things like that. But there are also, under those categories, if you want to think of it like that, some wave traveling behavior that we need to talk about. So let's pretend that you took a rope or a string or something like that, and you shook it up and down once. Now, you would have a wave travel, in this case, we'll say to the right at a speed of v. And this type of wave we call a pulse. So a pulse is basically a single lump of a wave that travels from one point to another point in space. Okay? Now, so that said, we also know, from our discussion about the properties of waves, that waves can interfere to create bigger or smaller waves. Now, we see that happen a lot in nature. And in fact, many of the waves that we see are actually what we call superpositions. Uh, if you remember the word superposition from a long time ago, that's typically what we call the addition of vectors. That's also what we call the addition of waves. You can add waves, you superimpose waves to create a more complicated wave. And this is what you're looking at right here. So this is an example of a wave packet. Now, so you actually have quite a bit of motion going on in here. For example, if you look at the packet itself, it actually consists of a whole bunch of waves that are sort of superimposed together. Okay, so you have the velocity of the packet as it moves to the right, which I'll call v sub g, which is the group velocity. Okay, now not only that, the actual waves that make this packet up could be bouncing back and forth on the inside. So you have, like I said, a number of velocities that are present. You have the velocity of the packet itself as it moves to the right, but then you have the velocity of these little waves as they bounce back and forth in the inside, and the velocity of the ones on the inside we call the phase velocity. Typically, it's written as v. This is a phi. Okay, so this is phase velocity. So we have a pulse, which is just a single wave, which may move. But then we can also, if you want to think of it sort of like this, group a whole bunch of pulses together to create a complicated packet, which travels at its own velocity, called the group velocity. And the waves within it travel at their own velocities, which would be the phase velocity. Now, so again, these are types of traveling waves. On the other hand, we have this. This is called a standing wave. Now it's still moving, even though when you see them, they almost appear as though they're stationary. And here's what's happening. So let's pretend that you have a string that sits sort of between points A and E right here. And what you're going to do is you're going to pluck it. Now, if that string has been positioned just right and it's been tensioned just right, then what happens is the wave that's created will travel and hit the other side. But when it hits the other side and part of it reflects off, the distance between where it started and where it ended up and where the reflection occurred happens to be some integer multiple of half wavelengths. Okay, so in this case, we have one full wavelength that sits here. Now, what happens is this wave starts here, hits here, bounces off, and as it returns, it sort of complements the original, and you end up with something that looks a lot like a standing wave or a standing stationary wave just sitting there sort of frozen in place. Now, in reality, it's actually vibrating, moving back and forth very quickly. But the trick here is that this distance between here and here, which we'll call L, L needs to be some integer multiple of half wavelengths. Okay. Now, so what happens if it's not? Well, it travels from here, makes its way over here, but it doesn't zero out at this rightmost boundary. So maybe it goes like this, and when it bounces off, you actually introduce interference. Okay, and in this case, the interference that you typically see is destructive interference. And over time, what that does is to rob the wave of its motion, and eventually the string goes to rest. Okay, so standing waves are only possible when you have the right conditions. Like I said, the distance between one side and the other side, we call these boundaries. So the distance between the boundaries is an integer multiple of a half of a wavelength. So for example, you could fit a half of a wavelength on here, which would look like this. You could fit a full wavelength on here, which looks like this. You could also fit, you know, 3/2 of a wavelength on here, which would look more like that, where you have one full wavelength and then a half at the end. So it might look something like this. Now, standing waves, it turns out, are incredibly important in physics because a lot of phenomena we can take and we can sort of freeze in time. So we freeze them in time between here, and then we look at the properties. Okay, we're actually going to take advantage of that here in a little bit. So that said, here's a little bit of terminology here that's useful, and this doesn't just apply to standing waves, but this applies to just waves in general. Is where you have a wave that's zeroed out, where it actually crosses, where it would be flat. Like for example, points A, point C, and point E here. Points A, C, and E we call nodes. A node is where the wave has a height of 0. And then you have points B here and points D, which you'll notice those are the sort of the peaks. So point B and point D we call antinodes. Okay, so nodes, like I said, are where the wave is 0 height, and antinodes are places where the wave is at its maximum height. So, like I said, two basic types of moving waves, if you want to think of it like that. You have a pulse, which would just be one empty packet, we'll say, that moves to the right. And then you have a more complicated superposition where you have a wave packet, which consists of a bunch of waves that are sort of stuck together, in which you have two distinct velocities, the group velocity and the phase velocity. And then, again, you have these properties in standing waves. And, if you were to sort of take a snapshot of a sine wave or something like that, you could assign nodes and antinodes to that as well. So that said, what I'd like to do is to move away from talking about those types of things. And, I'd mentioned, I think maybe last video before, I think actually last video, that since you have a wave that's traveling from point A to point B in space, it has motion, and if you have motion, you have kinetic energy that you can associate with it. So what I'd like to do now is to talk about the actual energy in a wave. We're also going to look at the power. Okay. So if you remember last lecture, I had written down sort of the general solution as a function of position and of time for the wave equation. And this was again a wave on a string, and it's in general true for any one-dimensional wave. And it looked like this: it was a times sine of kx plus or minus omega t. Now remember, plus refers to a wave that's moving to the left, and minus refers to a wave that's moving to the right. Now we also have relationships between k and omega and the properties of a wave. For example, k we call the wave number, and it's 2 pi over the wavelength. And omega is the angular frequency or the angular velocity, and it's 2 pi over the period. Or if you think of 1 over the period being the frequency, is 2 pi times the frequency. So as a wave moves from point A to point B in space, so let's just sort of draw us a little bit of a sine wave here. And again, I'm freehanding this, which means it's not going to be perfect, but we'll deal with it. So, maybe our wave looks like this. Not the perfect thing, like I said. So as this thing travels through space, moving, we'll say, to the right and along the x direction. In reality, we know it's moving is the material on, if we assume this is a string, is the material of the string, and it's just moving up and down. So remember, the bits of matter that make the string up aren't moving side to side. They're moving up and down. And that's where the energy of the wave is inside this up and down motion. Now, we can model the tension inside the string, okay, as that of a spring. If you remember our first lecture showing you that the solution for uniform circular motion for a spring and also for a pendulum, they all have the same solution in one dimension. Well, I mean, that's basically what this looks like right here. So you have, as this thing is pulled up, potential energy. So you have potential energy in it. If it's moving, you also have kinetic energy as well, which means that if we want to find the total energy inside this wave, we need to look at the potential energy and the kinetic energy that's present. Now, that said, our equation here is a function of both position and time. Now, the thing is, though, is that as this thing varies over time, the energy that's inside the wave, we'll say between points A and point B right here, we'll just use one wavelength as an example. The energy that's inside this wave is the same. Okay, it doesn't change. As long as we add it up over position. So over time, whether the wave looks like this, or this is busy going down or going up and this is busy going down, you're going to have the same total amount of energy. So what we can do, and this is something, a trick that's done frequently, is we can treat this as though it's a standing wave. This is between points A and B, and we're just going to freeze this in time. So we're going to let time equal to 0. And when we do that, what we've done is we've taken our equation here that has 2 active variables in it, and we've turned it into one that has just 1, which makes life easy. So in that case, it's just going to be a times sine of k times x. Okay. Now, so what I'm going to do is I'm going to sum up the total energy from here to here. That is the total energy in one wavelength. But I want to start with the potential energy first. Okay. Now, like I said, we can treat this like it's a spring. And the potential energy in a spring that vibrates along the y direction would look like 1/2 k times y squared instead of x squared. The issue that you have here is that k specifically refers to springs. But we know if something's exhibiting simple harmonic motion, that we can relate this k parameter to things like an omega. And if you think just specifically of a spring itself, we know the relationship looks like omega is equal to the square root of k over m. And you can go back and take a look at the very first video to see that. So what that means is that I can get rid of k and talk about things in terms of m and omega instead, which are general things, as opposed to k being a specific reference to spring. So I can write this as 1/2 times m omega squared y squared. Now, here's the deal though. What I want to do is to look at a single little element of mass, a single little dm here, and then sum it from A to B, which would be one wavelength. So at the end of the day, I'm starting at 0 along the x-axis, and then I'm ending up at lambda. So I'm just going to sum it over one wavelength. So this is going to be the potential energy trapped in this particular string that exists over one wavelength. And if you know how many wavelengths you have on, we'll say, your string, you can easily find the total potential energy. So the issue that you have here is, since we're dealing with a small little mass element, my m here isn't m, it's actually dm. So I have a very small amount of potential energy that sits in this thing. Okay, it looks like that. Now, so dm on a string, we know, is just lambda times dx. Okay, you can go back and you can look at the last video and look at the derivation for the wave equation. You can see exactly what I'm talking about. Likewise, we know what y looks like. Y looks like this. This is the general solution to, a spring. Now, last time we did a cosine. Sines work just as well, and you can prove that to yourself if you plug in this solution and try it in the wave equation. Or not the wave equation, but rather the spring equation. You'll see that it satisfies it. Basically, any sort of wholesome trig function like this we're okay with. So 1/2 dm here is lambda times dx. Omega is a constant, so omega squared. Y squared is going to look like a squared sine squared of k times x. Now remember, we've frozen this thing in time. If you look at the overall wave, again, the potential energy, when you add it up to the kinetic energy, the total energy is going to be the same. We'll see that here in a second. So if I integrate both sides, if I integrate du, what I'm going to end up with is the potential energy just for one wavelength. So I'm going to call that u sub lambda. Okay. On the right hand side, I have a whole bunch of constants. For example, 1/2 is a constant. The wavelength is a constant. Omega squared is a constant. A squared, that's another constant. So really what I'm integrating here is over one wavelength again, sine squared of kx dx. Now I'm going to make a substitution here. I'm going to call theta kx. So d theta is going to be k times dx. Now, once again, remember that this k right here is not the same thing as the k in the spring constant. It's the wave number. It's this k right here. This is what we're looking at. Okay, so if I make this change a variable, what I end up with is a 1/2 lambda omega squared a squared. Now I'm going to look at the limits of integration here in a moment, but this becomes sine squared of theta, and dx is just going to be d theta over lambda. So that lambda will come out, or actually over k rather. So that k comes out. So 1/2 lambda omega squared a squared over, now why is it lambda? Oh, sorry. It's foolishness. I'm so used to writing, so just for reference, this will help you if you go back and you look at other books. Mass densities a lot of times are written as lambdas. So that was a big mistake on my part. I really apologize for that. but I'm not going to change the video because it's what it is. We've been using mu, so we'll stick with mu. That's mu. Where's it at? A mu here. And I'll put my mu here. There we go. So 1/2 mass density, mu. Mu times omega squared times a squared over now k. That looks a lot better. So we have a sine squared of theta d theta. Now, let's look at our limits of integration. So when x is equal to 0, theta is equal to 0. And when x is equal to lambda, theta is equal to k times lambda. But look, k is 2 pi over lambda. So when you do this multiplication, this is just 2 pi. So this is the integral that we have to do. And it's not a bad integral to do. You can actually look this particular integral up. In fact, if you integrate sine squared of x dx, you get 1/2 x minus 1/4 sine of, let me get my little integrand sheet because I remember that much, sine of 2x right there. So this is what you get when you integrate it. Okay, now if you look at our limits of integration, on the bottom we have 0. Now sine of 0 is 0. Obviously x is 0. So when you do the bottom limit of integration on here, this is 0. But if you put the top one in, you'll have sine of 2 times 2 pi, which would be sine of 4 pi. And remember, any multiple of pi with respect to sine gives you 0. So this is going to be 0. But you'll have a 2 pi in your x, which means that at the end of the day, this integral is just pi. Okay, so our potential energy along one wavelength is going to be 1/2 times mu omega squared a squared pi, and then you have this 1 over k hanging out. Now remember, k is 2 pi over lambda, which means 1 over k is lambda over 2 pi. And when you plug that in, you get 1/4 mu omega squared a squared lambda. So this actually right here is the potential energy that's trapped along one wavelength as this thing oscillates. All right. So we're going to do the same thing now for kinetic energy. Let me borrow my my poorly drawn wave here. I'm going to take and paste it over here. Now, we're going to make the same sort of argument here for potential energy. Again, and I'm going to do it right this time, dm, our mass, is mu times dx. The issue that you have with potential energy, though, is that it's 1/2 mv squared. Now, the v here is the up and down vibration of the string. So v here really is just vy, or the derivative with respect to time of y. Now, y, remember, if you freeze this thing in place in time, is going to look like a times sine of kx. So obviously there's no time there. So what we're going to do here is we're going to take the derivative of the full y and then let time equal to 0. So the full y, remember, is a sine kx. And I'm going to use a rightwards traveling wave. It doesn't matter if you use a left one. But, you know, just from consistency, we're going to stick traveling to the right. And if I take the derivative with respect to time of y here, what you end up with is a minus omega out in front. The sign becomes a cosine. So this is minus omega times a times cosine of kx minus omega t. And when I freeze this thing in time at that instant, it is just minus omega times a cosine of kx. So what that means is that, again, if I look at a small little mass element as that thing moves up and down, that would be 1/2 This would be dm. dm is mu times dx, and this is v squared. V squared is going to be minus omega times a times cosine of kx squared. Now, the square is going to make this positive. Again, if you had chosen going to the left, this would be a plus here instead of a minus. You're going to get exactly the same answer. So you have a 1/2 mu omega squared a squared. And then what you're integrating here, and we're going to get to that here in a second, is going to be a cosine squared kx dx. Okay, so again, if I integrate over one wavelength, that's case of lambda. 1/2 mu omega squared and a squared are all constants. The integral that I need to do is cosine squared kx dx from 0 to 1 wavelength. We're going to make exactly the same substitution. That is, theta is equal to k times x. When you do that, we know that you get a k in the denominator over here, like that. Our limits of integration go from 0 to 2 pi, and we have a cosine squared of theta d theta. Now, it turns out that if you look up on an integration table how to integrate this, it looks almost identical to how you integrate this, with one exception. If you do a sine, or if you do a cosine here, it makes it a plus. So if this is a cosine, this is a plus. And so you're going to get the same answer, it turns out. This is pi when you do that. And when you plug in the fact that k is 2 pi over lambda, and you manipulate things around, again, you get 1/4 mu omega squared a squared times lambda. Now, this is the same. This is the same as what we got for the potential energy. And that should make sense. This is periodic, which means that at any given time, you have energy being exchanged between k and mu, or k and u rather, the potential energy and the kinetic energy. But when you look at the overall average over one wavelength, you're going to have the same amount of energy involved in moving the wave as you do it being stored in the wave. So our total energy, okay, which would be our kinetic energy plus our potential energy, is just going to be twice this, or 1/2 mu omega squared a squared times lambda. Okay, so as you can see, the total energy in this thing depends upon the amplitude, but it also depends upon the wavelength, which should make sense. If you have a longer wavelength, you have more string to store energy in, or more wave to store energy in, which means that you're going to have more energy in it. If you have a much higher wave, if the amplitude of the wave is bigger, what that means is that the energy is going to be substantially more, to the power of, or to the tune of amplitude squared, which means if you double the height of your wave, you increase the amount of energy on the inside by a factor of 4. For those of you that have ever surfed before, that's the reason why there's so much power inside one of the bigger waves in comparison to one of the smaller waves when it hits you. That's because of where all the energy is. Okay, so it's a tremendous amount of energy there. Now, we derive this sort of with the transverse wave, but this is true for longitudinal waves and also for torsional waves as well. Now, what I would like to do is to take a look at the power that's trapped inside this wave. So power is just energy over time. And so we're going to look at it over one period. Okay. So over one period, this would be 1/2 mu omega squared a squared. And I'm going to put the period under the wavelength because 1 over period is the same thing as frequency, which means that if I look at this, this is just lambda times the frequency. And hey, the velocity of a wave is lambda times f. So this is just the velocity of the wave. So the power inside your wave along one lambda, or one wavelength, is 1/2 mu omega squared a squared times the speed of the wave. So we have two good results here. We have the total power. Whoops, I didn't want to do that. Actually, what I wanted to do was this. We have the power inside the wave, and we also have the total amount of energy inside the wave. So what I'd like to do now is to take those two equations and just sort of examine this problem right here. We have a string that has a mass density of 25 grams per meter. Now, one side of the string is attached to a string vibrator which swings with an amplitude of 10 centimeters. And the other side of the string goes over a pulley, and on that side you have 150 grams hanging off of it. So that's what's giving it its tension. Now, there's 2.5 meters that sits between where the string attaches to the vibrator and where it hits the pulley. Now, the reason why I'm pointing that out is because at this point right here, the height of our wave is 0. And at this point over here, where the vibrator sort of ties to the string, this point right here is 0 as well. So these right here are nodes. Now, what we're going to do here is to let this thing vibrate to put exactly one wavelength along the string. So we have a standing wave here that's going to look something like this, which means that not only do we know the distance between the vibrator and the pulley, we also know the wavelength of our wave. The wavelength of our wave here is 2.5 meters. Okay, now we have the amplitude that this thing is being vibrated at. It's 10.0 centimeters or 0.100 meters. We have the mass that's hanging off the end over here, which is 150 grams or 0.15 kilograms. We have the mass density, mu, which is 0.025 kilograms per meter. Now, what we're trying to find is the frequency that's required to put this one long-standing wave from here to here. So, we're going to need to find the frequency. Now, once we have that frequency, what I'd like to know is how much energy is inside that wave, and also how much power is being supplied by that string vibrator to make that wave occur. So we want to find E, and we want to find P. Now we're given, like I said, quite a bit of information here. We have mu is 0.025 kilograms per meter. We have the amplitude, which is 0.100 meters. We have the wavelength, which is 2.5 meters. Excuse me. And we also have the mass that's hanging off the end, which is 0.15 kilograms. Now that's relevant to us because that's what's tensioning the string. So we have what we've been given. We have what we're trying to find. So let's take a look at the problem. So what we're going to want to do is to find the frequency of the string vibrator before we actually do, the energy and also the power. And we know that V is equal to lambda times F. Now we have lambda. We can find V based off of the properties of the string. And that'll enable us to find this F. Okay, so what's V? Well, if you go back and you look at the previous video, that's the square root of the tension in the string divided by the mass density along the string. Now, the tension we know comes from this mass that's hanging off the end. So this is going to be the square root of mg over mu, or the square root of 0.15 kilograms times 9.8 meters per second divided by 0.025 kilograms per meter. Now, if I do the math here, let me look at this real quick. So we're going to take the square root of 0.15 times 9.8 divided by 0.025. I get 7.67 meters per second, or actually, and I'll just write out a few significant digits here, 668 meters per second. Okay, so there's my V. So I've been given my V. I already know what lambda is. I can find frequency. Frequency is just V over F, or the 7.668 meters per second divided by, over lambda rather, 2.5 meters. So let's see here. 3.07 hertz. So it needs to vibrate about, let me go back down there. Sorry about that. It's just sort of fat fingered with my palm there. So if this thing vibrates about 3 times a second, it's going to create the wave that we're looking for. All right. So let's see here. We have 2 sig figs, 2 sig figs, 3 sig figs, 2 sig figs at the end of the day, 2 sig figs. So for our frequency, we are looking at a frequency of about 3.1 hertz. So there's the answer to that. Now, next we want to find the energy. So if you remember, back here, we had come up with equations for both the energy and the power. Let me just snipe those. Whoops. Put it here. So the energy inside this wave as it vibrates, since this is one wavelength that's along the entire wave, would be 1/2 mu omega squared a squared times lambda. Now remember, omega is 2 pi times f. So we have our frequency here, which means that we can easily put this in here and sort of fill things in. 1/2 mu, we know what that is. Omega would be 2 pi times f, that's squared, a squared times lambda, or 1/2. Mu is, actually, let me get all my data here, and I'm just going to copy it and paste it over here. Just so I can just make life easy. All right, so mu here is 0.025 kilograms per meter. This is 2 pi times the frequency. The frequency we got is about 3.07 hertz. Gotta square that. The amplitude is 0.100 meters. Gotta square that. And the wavelength is 2.5 meters. That's something we were given. So let me plug this in here. Let's see. 0.5 times 0.025 times 2 times pi times 3.07. Got to square all that. then times 0.1 squared, then times 2.5. And I get 0.116 joules is trapped inside there. Or if I keep the two sig figs, 0.12 joules. Now the power, we could go through this rigmarole right here and do this long thing again. Or again, just note the fact that the power is the energy over the period, since it's one period for that whole thing, which would be 0.116 joules times the frequency. And the frequency we found to be about 3.07 hertz. So if I take this and multiply it by 3.07, I end up with about 0.36, if I round, watts. So that's how many joules per second. Oops, again, I don't know what I'm doing here. That's how many joules per second that string vibrator is going to have to supply to the string in order to make the standing wave act the way that it does. Now, so we're almost to the end of our discussion about waves, but there are one or two little topics that I want to briefly bring up just for completion, and also because we'll be seeing them in some degree later on. And the first thing I'd like to bring up is the fact that if you remember towards the end of University Physics 1, we sort of introduced the concept of pressure. And pressure, remember, is force over area. And the reason why pressure was such a big deal is because when you add more and more levels of detail to stuff, you stop talking about force and you start talking more about force applied over area, because things in reality have area to them. So the same goes for power. So, for example, I can talk about, how much power something puts out or how much energy something has. But when we talk about power, especially for a wave, remember a wave travels. If you go back and you look here in our standing wave, or not our standing wave, but in our the wave that we're looking at here, the power depends upon how fast the wave is moving. So there's motion involved, right? So waves travel outwards from where they're created, and by travel outwards, the correct term for that is they propagate. Propagation. So propagate means to travel from point A to point B as a wave. So if you think, for example, of creating a wave here, like you drop a rock in the water or something like that, what you have is this circular wave. Dagnabbit. You have the circular wave that travels outwards like this from the point in which it was created. So as it goes, it's traveling this way out. Now, many of the things in nature that create waves, instead of having a circular shape to them, are spherical. A good example of which would be a star, like the sun's. The sun is basically a sphere. So, if you want to talk about, for example, how much energy is falling on the Earth due to the sun, you would, instead of talking about power, need to talk about power being distributed over area. And that is called intensity. Intensity is defined as power over area. Now, so if you think about the sun as a specific example, the area that all of that energy, all of that power over time, or not power over time, but all that energy over time, we'll say, is traveling through, would have the shape of a sphere at any given point in space. So, for example, if I wanted to know how intense the sunlight was here, what I would do would be to capture all of the energy that's leaving the sun over time in this spherical shape. So typically the way we write our intensity, or at least the total intensity, would be power over the area of a sphere, and the area of the sphere is 4 pi times r squared. Now, just as an example, I want to consider the sun, which does put out about 3.846 times 10 to the 25th watts of power. Now, let me make sure that number is right. 10 to the 26, actually. Yeah, the 25th didn't look right. So this is the 26. Okay. Now, the Earth is about 1.5 times 10 to the 11th meters away from the sun. This is called an astronomical unit. We introduced this concept last semester. What I want to know is what's the intensity of the sunlight at the Earth. Now, if you want a good feel as to what intensity is, if you want to think about hearing, for example, with sound, in the realm of sound, intensity is what you would think of as loudness. So we hear using our eardrums. That's where the sound enters the ear and starts to do its work. And an eardrum is just a little membrane of skin, if you want to think of it like that, that has an area. So what happens is some of the energy of the wave that enters your ear falls over the area of your eardrum and causes your eardrum to vibrate. Okay? Now, if there's more energy there, then the vibrations are going to be more extreme. And as a consequence, the intensity is going to be more. And what you hear is going to be louder. Now, with sun, or with light in general, the intensity of sunlight we think of as brightness. So if you think of light leaving the sun as little bundles of rays, like little arrows, and each arrow carries a little bit of energy over time with it, then the more bundles of light that fall into your eyes, well, the brighter something is going to be. So intensity is more along the lines of what we experience and what we measure, as opposed to directly measuring something like power or energy. Those are all things that are indirectly measured. So here, what we're really asking is how bright is the sunlight at the Earth? Okay. Now, so we have been given the amount of power that the sun puts out, which is 3.846 times 10 to the 26 watts. We're also given how far away the sun is from the Earth, which is 1.5 times 10 to the 11th meters. What I'd like to find here is the intensity. Now, the sun, like I said, is a sphere. It puts out light in a spherical manner, which means the intensity here is just the power over the area. And the area of the sphere is 4 pi times r squared. So that would be 3.846 times 10 to the 26 watts divided by 4 times pi times r squared. That's 1.5 times 10 to the 11th meters squared. So if you perform this calculation here, let me do it real quick. Let's see, 3.846 times 10 to the power of 26 divided by 4 times pi times 1.5 times 10 to the 11th meters squared. Okay, that was weird. A little bit of a typo there. Give me a second here. Then I got to square that. I get 1,360 watts for every square meter. Now, this is pretty relevant. For example, think about solar power. So now, to be clear, we haven't taken into account, the action of the Earth's atmosphere or anything like that. But when you generate electricity via solar power, what you do is you want the sunlight to fall over the area of your solar panel. So sunlight falls onto your solar panel. It has an intensity. It's bright. It falls over the area. And if you look at this right here, intensity times area is power. So what this does is, through something called the photoelectric effect, is it generates power. And the power we have to put through some sort of inverter and sort of massage it a little bit. And it comes out at the end of the day as household electrical power, which is AC current, which is something we'll be talking about towards the end of the semester. So many solar cells have efficiency ratings. The efficiency of solar cells is really not that great. In general, it's less than 30%. In fact, just for the heck of it, I looked up one. One of the best ones in the market is called a SunPower. It's Maxeon 3, I think this is what it is. SunPower Maxeon 3. Now, this thing is, its dimensions are 1.046 meters by 1.690 meters. So that's its area. And it's 22.6% efficient. So what that means is that only about 22.6% of the sunlight falling onto this panel is available to generate electricity, and that's pretty common. So 30% is, I'm not going to say unheard of, but it's incredibly expensive. So here, if I look at the area, 1.046 times 1.690, it's about 1.76 or 1.77 square meters. So my area here is about 1.77 square meters. So this right here, like I said, barring the presence of the Earth's atmosphere, this right here is how much energy is falling on the surface of the Earth or into the atmosphere of the Earth every second for every square meter that's there. So if I wanted to know how much power is being delivered, that again would be the intensity times the area. And if I do that calculation using that intensity in the area that I just got, it's 1360. It ends up being about 2,404 watts. Now, the issue again that you have here is that this is only about 22.6% efficient. So if I multiply that by 0.226, I get 543 usable watts of energy from that solar cell before it's been processed, which always involves some sort of loss. Now, if you were to look at what these solar cells are actually rated at, they're rated at about 400 watts, which is probably about right, considering the fact that you have loss due to the Earth's atmosphere, and you have this additional efficiency loss. Okay, so as you can see, you can harness this energy, through devices that will turn intensities into usable power. Now, so that said, the very last topic that I want to talk about, and I'm just going to briefly talk about this to introduce this as a concept, is something called the Doppler effect. Now, in mechanical waves like the ones that we've been talking about so far, you see the Doppler effect present all the time. If you've ever been walking along the road and had some car with bad exhaust come up behind you and pass you, you actually hear the pitch of the exhaust change. As it comes towards you, maybe you hear ee, and as it passes, it goes meow. So you hear this change in pitch. Now, pitch is what we perceive of as frequency. Okay, so it's actually frequency. So I want you to think of a situation where you have, I don't know, some person standing on a platform in the water. So here they are, they're standing here, and what they're going to do is they're going to jump up and down with the frequency. I'm going to call this F sub s. This is the source of the wave. Now, as this person jumps up and down on this platform that's in the water, what they're going to do is they're going to generate waves that travel outwards. This way and also this way. We're just going to look at the ones that are going on this way to the left. Now, these waves are traveling at a frequency of F sub s. They have a wavelength, which is the physical distance between them. And they have a speed, which I'm going to call, since this is a wave, the velocity of the wave, or the speed of the wave. Now, I want you to imagine sitting in a boat. So maybe here's a boat. And what you're going to do is you're going to take your boat towards the person who's making these waves. And your boat is traveling at a speed of v. Now, as you travel towards the person who's making the waves, if you look at the waves, you actually, if you've ever been boating, you know that if you drive towards the waves that are coming towards you, your ride gets really bad. It goes bump, 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 as opposed to maybe just the gentle bump that the wave normally would be giving you to begin with. So what you're saying as you travel towards these things are the peaks of the waves more frequently. And the reason why you're seeing them more frequently is because you're driving towards them. So more frequently means a higher frequency, which means that you, as an observer, you observe a frequency that's not going to be the same as the sources because of your motion. So if you think about the relationship between the speed of a wave, its wavelength, and its frequency, and you think about the situation that's going on here, both the observer and the source are going to agree about the distance between the peaks. We agree about the wave length. What we disagree about is the frequency, and that's a consequence of my motion. So as I move this way, I see waves moving towards me with a speed of VW, which means that I have an effective velocity, or the waves have an effective velocity of my speed plus their speed. Okay. Now it's this effective velocity that's giving me the frequency that I see, which means that, if I were to say, I don't know, divide this by lambda, like that. Then on the left-hand side, if I divide it by lambda, I get the frequency that I observe. On the right-hand side, I have a v over lambda plus a v of the wave over lambda. Now, this is the actual velocity of the wave in a medium if you were stationary relative to it. So this right here would be the frequency of the source. So my observed frequency that I see is my speed over the wavelength plus whatever the source's frequency is. Now, I'm going to massage this a little bit further by noting the fact that lambda, again, is just f, or lambda is just v over f. So if I put in v over f here, or the velocity of the wave rather over f, if I put in the velocity of the wave over f here, what that does is to put a frequency of the source, my velocity in the boat, or the velocity of the wave, plus the frequency of the source. So I can actually find a relationship between the frequency that I see, the source's frequency, the velocity that I'm traveling at, the velocity of the wave, and that. Now, typically the way this is written is the following. Now, if I were to move away this way, I would see the peaks less frequently rather. And that would be analogous to me putting a minus sign here. Okay. So this right here is called the Doppler effect, and it turns out that it doesn't just work for water waves. Like I said, it works for sound waves as well. And as we're going to discover towards the end of the semester, it works for light waves too. So as an easy example, I want you to think of a person who's standing stationary and they're playing a saxophone. And this is a mid C. So the source frequency of our musical note is 261.63 hertz. Now, I want to know how quickly I would need to be moving towards the source to, instead of hearing a musical note of a C, a musical note of a D. A D has this particular frequency. Now, in air, at standard temperature and pressure, which we'll be talking about what that means later on, the velocity of sound is 340 meters per second. What I would like to find is what my velocity needs to be in order to make this happen. Now, if you look, let me grab my little sheet here. If you look at the equation that I just came up with, the observed frequency is related to the source frequency through, and I'm going to write it this way, V over VW plus 1, because this is just a little bit easier to work with. I'm trying to find V. If I solve for V, that's going to be F naught over F sub S minus 1 times V sub W. So let's plug stuff in. 340 meters per second. F naught is 277.183 hertz. The source frequency is 261.63 hertz. Subtract 1 away from that. And when you do your math here, you end up with, let me see, calculator here. Minus 1. 20.2 meters per second. So if you think about how fast cars go, 20 meters per second is incredibly reasonable for the speed of a car. So it's entirely possible for you to pass somebody who's playing a saxophone, and inside your car, as you move towards them, you hear the musical note of D, and they are actually playing a C. Now, we'll be talking more about the Doppler effect later on, like I said. But one obvious use for this is something called Doppler radar. We use sound, or not sound, but we use light. We bounce light off of, humidity in the atmosphere, and the return tells us information about the motion of that humidity, and as a consequence, clouds and stuff like that. And that's it for today's lecture. And I will see you in the next big lecture, and that's going to be the beginning of thermodynamics. I'll see you then. Bye.